Yogendra Kenti, an assistant professor, and his colleague discovered that COVID-19 may develop blood clots. This is due to autoimmune antibody that were circulating in the blood was attacking the cells and triggering clots in the arteries, vein, and microscopic vessels, which could lead to life-threatening events such as stroke. This blood clot can occur at a microscopic level where it may restrict blood flowing into the lungs and impairing the oxygen exchange due to COVID-19. So, the way that these hot arm thermal actuators are able to help in this situation is that research can be done at a microscopic levels where MEMS device is functioning as a microgripper. This microgripper shall be able to grip a couple of individual red blood cells so that researcher can do experiment about how COVID-19 virus affects the individual red blood cells.
Assalamualaikum warahmatullahi wabarakatuh. A very good evening. My name is Hafiz Zikri bin Manasir. I'm for Architecture Electronic Engineering. Today I would like to present to you about monometallic hot and cold arm thermal actuator using gold material. This is a MEMS device that use a fixed free configuration for body condition where it's anchored around here. So by using a gold material as a core material, so this device was able to achieve the maximum deformation of the around 9.6 micrometer when it has a fixed point around here to anchor the stress that will be developed around this area, that it can increase the maximum stress at the 1.2 gigapascal at the 500 degrees Celsius. So that's all for me for my slide presentation. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Asrul Izwan bin Abdullah. So in this part, I will explain about our thermal actuator design by using zinc materials. For this thermal electric simulation is to observe the current flow to heat up the design. So in this design, we can see the design heat up from hot arm area to cool arm area. It is because high potential voltage is at hot arm area. For the static structural simulation, if you can see at the graph, if we increase the temperature from 0 until 400 degrees Celsius, I put 400 degrees Celsius, it is because the 400 degrees Celsius is the melting point of the zinc. So if we increase the temperature, the maximum deformation of the design also will be increased from 0.93681 micrometer to 16.096 micrometer. It can be explained when we heat up the zinc. Zinc molecule will move faster and faster as energy is particle increased. We weaken the intermolecule force between them, thereby expanding the material, and after that, it can able to increase the deformation of the design.
Assalamualaikum, my name is Akil Lukman bin Abdul Rashid. Today I would like to present my project E thermal actuator for a material of silicon. For the introduction, as we know, thermal actuator is a type of non-electric motion made of components such as piston and thermal sensitive material that can produce linear motion in response to change in temperature. At the below, we can see the structure of the design. So we use two analysis system in NC software, which is thermoelectric and statistical structure. There are 4 parameters to do this design, which is electric voltage, temperature, stress and strain, and deformation. This is our result at the right. As a conclusion, we have achieved our objective to get almost the same result as the reference journal. Therefore, the silicon material can achieve melting point at 1412 Celsius, which is good thermal condition. Next, we are also able to observe maximum deformation, stress and strain when applied at different temperatures. This shows the relation temperature is directly proportional to the deformation of the material. Finally, we can see the difference in output if we choose different material. So that is all for me. Thank you.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Amir Hafizuddin bin Musa from RK86 Electronic Engineering. Here I would like to present to you about hot arm thermal actuators. So the basic principle of this device is that it will bend when it is heated. The way we produce the heat is by running a current through the device. The more the current, the hotter it gets. The hotter it gets, the more it deforms. This MEMS device uses fixed free configuration where it has an anchored point around here. And by using aluminum as the core material, the device was able to achieve a maximum deformation of 12 micrometers when it is heated around 300 degrees Celsius. And because it has a fixed point around the anchor, stress would be developed around this area where it can go up to a maximum of 1.3 gigapascal at 300 degrees Celsius.